Okay, in this section here, I'm going to talk about the titration of a weak acid with a strong base. Previously, we calculated the titration curve for the titration of a strong acid with a strong base. And let's say we use the same strong base to titrate two different solutions of equal molarity, one a strong acid and the other a weak acid. We're going to get titration curves with two features in common. Number one, the same volume of base is required to reach the equivalence point in both cases. And number two, the portions of the curves after the equivalence points are substantially the same. There are some important differences, though, between the two titration curves prior to the equivalence point. And you can see this in my figure here. Again, this is the curve for the titration of a weak acid with a strong base. Notice that our initial pH is higher, and this is because the weak acid only partially ionizes. Okay, where if you have a strong acid, remember there's complete dissociation. Also, notice here at half of the neutralization point, okay, our pH is going to be equal to the pKa. At this point, we have a buffer solution in which the concentrations of the weak acid and its conjugate base are equal. Okay. Also notice that at the equivalence point, the pH is greater than 7, and this is because the anion of the weak acid will hydrolyze. The steep portion of the curve just prior to, okay, and beyond the equivalence point is confined to a much smaller pH range. Okay, so if you need to get out the other curve for the titration of a strong acid with a strong base and just compare the two curves. Also, we have to choose an indicator whose color changes brackets the pH at the equivalence point. And remember, for this particular titration, this is going to occur in a basic solution. Generally, the midpoint of the pH range in which the indicator changes color must be well above pH of 7. So I think the best thing that we can do here is I'll go ahead and repeat what I said before, and then we'll just go ahead and do a few calculations. So again, the initial pH for a titration curve for the titration of a weak acid by a strong base is going to be higher, and that is because the acid only partially ionizes. At half the neutralization point, the pH is going to be equal to pKa. Remember, the solution is a buffer, so at this point here, the concentrations of the weak acid and conjugate base are equal. The pH is greater than 7 at the equivalence point, again, because the anion of the weak acid will hydrolyze. The steep portion of the curve just prior to and beyond the equivalence point is confined to a smaller pH range. And again, I won't repeat what we said about choosing the indicator. We did talk about indicators in a previous lecture video. Let's go ahead and move to a problem here. When we calculate the titration curve for a titration of a weak acid by a strong base, we have 6 different types of calculations that we need to perform. Number one, we have to determine the initial pH, and this is going to be due to the ionization of the weak acid. Number two, the early stages of the titration, the ionization of the weak acid is going to be suppressed by a common ion. Okay? So basically we have, and also we have a buffer situation. In the pH range where pH is equal to pKa, plus or minus 1, we have the buffer solution. So we're able to use the Henderson-Hasselbalch equation. At half the neutralization point, the pH is equal to the pKa. At the equivalence point, hydrolysis of anion, okay, is taking place. Of course, the anion is the conjugate base of the weak acid. And then finally, beyond the equivalence point, the pH is going to be determined by the excess base in the solution. So here is the problem that I would like to do. we're going to calculate the pH at the following points in the titration of 20 milliliters of 0.5 molar acetic acid with 0.5 molar sodium hydroxide. So we're going to calculate the pH before we add any sodium hydroxide. And of course, the pH there is going to just be based on the ionization of the weak acid. We'll calculate after the addition of 8 milliliters, 10 milliliters, 20 milliliters, and 21 milliliters. It really is in our best interest with these types of problems to determine the equivalence point volume first, because, you know, again, the calculation before the addition of sodium hydroxide is going to be different than the calculations anywhere before the equivalence point. At the equivalence point, different type of calculation, and then of course beyond the equivalence point, again, another type of calculation. So it's really best to determine the equivalence point volume, and then that way we know what area of the titration curve we're in. Because again, we're always interested in the pH before addition of base, in the buffer region, okay, before the equivalence point, at the equivalence point, and then of course after the equivalence point. So our first step to this problem, we will determine the equivalence point volume so that we know exactly where we are in the titration and then can calculate the pH at each point. Okay, so first thing I want to do is determine the equivalence point volume. And I have to make sure that I write my balanced equation, okay, for this particular reaction. So we have acetic acid being titrated with sodium hydroxide and to produce acetate ion and water. Okay, the important thing here is that we have a 1-to-1 ratio between acid and base. Okay, so I'm going to determine the equivalence point volume here. So let's see, I know that I have 20 milliliters of 0.5 molar acetic acid. And so I'm going to determine the moles of acetic acid. And that's just going to be the molarity times the volume. And that's going to give me 0.02 liters times the molarity of the acid, which is 0.5 molar. Okay? So let's see, the moles of acid are given by, let's see, 0.02 times 0.5. We end up with 0.01 moles of acetic acid. Okay, so at the equivalence point, we have, again, we have a 1-to-1 mole ratio, okay? So this means that all of the acid is going to be reacted with the added base, okay? So we want to determine how much base, or how much sodium hydroxide is needed to neutralize all of that acid. So let's see, I'll start off here with my 0.01 moles of acetic acid. I'm just going to represent that by HA. It's a little easier to write. And then I use my balanced chemical equation. I have 1 mole of acetic acid for 1 mole of sodium hydroxide. So that means it's going to take 0.01 moles of sodium hydroxide, okay, to completely neutralize the acid. So now I can determine the volume of sodium hydroxide needed. And so the volume is just going to be the number of moles over the molarity of the sodium hydroxide. So that's going to be 0.01 moles over, let's see, it's 0.5 molar, 0.5 molar. And that's going to give us 0.02 liters, which should be 20 milliliters. So our equivalence point volume equals 20 milliliters. So, for example, in part B of the problem, I'm asked to calculate the pH after the addition of 8 milliliters, and in part C, after the addition of 10 milliliters. So that is before, both of those are before the equivalence point. Part D, it tells me after the addition of 20 milliliters, well, that is the equivalence point, and then after the addition of 21 milliliters, that is beyond the equivalence point. So now that we have our equivalence point volume, let's go ahead and go to part A of the problem. Again, we're titrating 20 milliliters of 0.5 molar acetic acid with 0.5 molar sodium hydroxide. So we want to calculate the pH before the addition of the sodium hydroxide. Well, this is the pH of the 0.5 molar acetic acid. It's the initial pH. Because the acid is weak, we have to do an equilibrium calculation for the hydronium ion concentration using an ICE table. So then we'll be able to determine the pH of the hydronium ion. So let's go ahead then and write the reactions. So we have acetic acid plus water, okay? And again, this is before the addition of any hydroxide ion, okay? So we'll go ahead and set up our ICE table, and the initial concentration is 0.5 molar, and of course this is 0, 0. Actually, this is not exactly equal to 0 because we have the autoionization of water, but in these cases we neglect it, okay? If you get into quantitative analysis, then you would need to include that in your equilibrium calculations, but we don't do that here. So this is going to be minus some amount x plus x plus x, and then at equilibrium we have 0.5 minus x, and then just x and x. Now, we know that Ka for acetic acid is equal to 1.8 times 10 to the minus 5. You're either given that or you look it up, okay? And so I'll go ahead and write the equilibrium constant expression over. So I can go ahead then and write that as x times x over 0.5 minus x. Now, what we're going to do here is we're going to assume that x is much less than 0.5 molar, than the initial acid concentration. We'll check our assumption a little bit later, but this is going to allow us to simplify this expression, okay? So now we have x squared over 0.5 molar. So now we can solve for x, okay? And we end up with x being equal to 3.0 times 10 to the negative 3 molar. Okay, I'm going to go ahead and check this assumption, okay? Again, we want less than 5%, okay? So we're going to take x and divide it by the initial acid concentration, okay? And then multiply by 100. So we have 3.0 times 10 to the negative 3 divided by 0.5 times 100. And that is going to give us, let's see, that's 3, okay, to the negative 3 divided by 0.5 times 100. And so we're okay. This is 0.6%, okay? Another way we can check this assumption, too, is what we're saying is that 0.5 minus x is approximately equal to 0.5. So 0.5 minus 3.0 times 10 to the negative 3 is going to give us 0.5 minus 3 to the negative 3. It's going to give us about 0.5 molar, okay? So we know that X is equal to the hydronium ion concentration. So now what we can do is we can determine our pH, and our pH is equal to the negative log of 3.0 times 10 to the negative 3, and that gives us a pH of 2.52. Okay, so I'm going to go ahead and grab another sheet of paper, and we'll keep track of this so we can indeed sketch our titration curves. So this here is the volume of NaOH, of sodium hydroxide added, and the pH. So before sodium hydroxide is added, our pH is 2.52. Okay, so I'm going to put this aside so that we have it in for our later calculation. That way we can keep track, and then we'll just go ahead and plot the pH versus the volume of titrant added. Okay, let's go to part B here. And this is after the addition of 8 milliliters of 0.5 molar sodium hydroxide. This is before the equivalence point, and what we have is substantial concentrations of both acetic acid and acetate ion, and we have a buffer situation. What we need to do is we need to first do a brief stoichiometry calculation, and then we're going to be able to use the Henderson-Hasselbalch equation to determine the pH after this 8 milliliters of sodium hydroxide is added. So let's first determine the number of moles of hydroxide ion that has been added. Okay, so what we have is we have 0.008 liters. You can use millimoles, okay, or moles. All right, I'm just going to go ahead and use moles. And of course, what we have is we have 0.5 moles, so the molarity of the sodium hydroxide per liter. Okay, and this is going to give us 0.004 moles of hydroxide ion that has been added. Okay, so here's what we have at this point in the titration. So I have my, let me go ahead and write my reaction plus hydroxide ion. That's going to give us water plus acetate ion. So the calculations before that equivalence point, okay, again, we have a buffer situation, so they're going to be the same. This is why it's really advantageous to determine the equivalence point volume, okay, before going ahead with any of these problems. Obviously, on a test, I'm not going to give you a whole titration curve to calculate. I might ask you what the pH is before addition of base or acid, before the equivalence point, at the equivalence point, or after the equivalence point. So this is what you need to know. You need to know these types of calculations. So you have to think about the chemistry that's taking place here. Okay, so let me see what I have. You know, if you don't mind, I'm going to adjust this camera a little bit because I really don't like the way I'm not getting enough space here. Let me see here. And let me move that. I think that's going to be a little bit better. Okay. All right. Sorry about that. So anyway, the initial amounts in moles. Okay, so our initial amounts, we have 0.01 moles of acetic acid. Okay, and obviously 0 here and 0 here are approximately equal to 0, right? And then our added moles, added hydroxide ion, that's going to correspond to 0.004 moles, okay? And then the changes are going to be, because we have to calculate how much acetic acid we have left, and then we also need to calculate the number of moles of acetate ion. So this is going to be minus 0.004 moles. And of course, all of the hydroxide ion will be consumed. And then of course, in this case here, this is going to be plus 0.004 moles of acetate ion. Okay? So after the reaction, Okay, we're going to have 0.006 moles of acetic acid left. And of course, oops, I should put that over here. 0.06 moles of acetic acid left, 0 hydroxide ion, and we're going to have 0.004 moles of acetate ion. So now we're ready to use the Henderson-Hasselbalch equation, and that's equal to the pKa plus the log of the acetate ion concentration over the concentration of acetic acid. Okay, and the pKa then is just a negative log of 1.8 times 10 to the negative 5, which is Ka. So we have pH is equal to 4.74, that's pKa, plus the log. Now remember, I could go ahead and divide the number of moles of acetic acid and acetate ion by the total volume of solution, which at this point would be 28 milliliters. But remember, that's going to cancel out here. So I only need the number of moles, okay, of each, 0.0060. And what I end up with then is a pH equal to 4.57, okay? So after the addition of 8 milliliters of 0.5 molar sodium hydroxide to 20 milliliters of 0.5 molar acetic acid, I have a pH of 4.57. So let me go ahead and record that right here, because again we want to calculate the titration curve. So I have 4 point, great, I just forgot what that was, 4.57 as a pH, okay? So now let's go ahead and go to part C, okay, of this problem. So in part C, this is after the addition of 10 milliliters of sodium hydroxide. Well, this is why it's important to calculate the equivalence point volume. The equivalence point volume is 20 milliliters. So here we're at the half neutralization point. Okay, so, and I told you that the pH is equal to pKa at that point, okay? But let's just go ahead and let me write the reaction again. Plus OH is going to give us water and, of course, acetate ion, okay? And so our initial amounts here, initially we have 0.01 moles of acetic acid, 0 here, and of course 0 here, or approximately equal to 0. So I have now added, okay, 10 milliliters of hydroxide ion, so that's going to be 0.005 moles of hydroxide ion. And then our changes, we're going to have the 0.005 moles of hydroxide ion is going to consume 0.05 mole or 0.005 moles of acetic acid, okay? And of course all of this is going to be consumed, and then we're going to end up with 0.005 moles of acetate ion in the solution. And then after the reaction, we're going to have 0.10 minus 0.005 is going to be 0.005 moles of acetic acid. And of course here we're going to have 0.005 moles of acetate ion. So as you can see, both of these concentrations are equal, okay, at the half neutralization point. So I'll go ahead then and put this into the Henderson-Hasselbalch equation. So the pH is going to be equal to pKa, which is 4.74, plus the log of, here we have the number of moles of acetate ion and number of moles of acetic acid. And this here, okay, is just equal to this ratio here is equal to 1, okay? So log of 1 is 0. So our pH at this point is equal to 4.74. So that's at that half neutralization point. So let's see, after 10 milliliters, our pH is 4.74. Okay? Now, let's go on to, let's see, we did A, B. Let's go into part D. Okay? And here's what we have in part D. In part D, this is after the addition of 20 milliliters of sodium hydroxide. And this is the equivalence point. Okay? So what we've got here is we've got 0.01 moles of acetic acid and 0.01 moles of sodium hydroxide have reacted to produce 0.01 moles of sodium acetate in 40 milliliters of solution. Remember, we started out with 20, added 20 milliliters of sodium hydroxide, so we have a total volume of 40 milliliters. Okay, so now we have to determine the molarity of the solution. Remember, all of the acid, all of the acetic acid has been consumed. Okay, so now we're just left with the acetate ion. Okay, so let's see what we have here. We have 0.01 moles of acetate ion, okay, over 40 milliliters, or 0.040 liters, okay, and that's going to give us a concentration of 0.25 molar, of the acetate ion, okay. So now at this point then we have to, we have Kb, okay. Let me go ahead and write the reaction here, okay. So what we have is here we have acetate ion, okay, and in water, and that's going to produce acetic acid, okay, plus, so we have this equilibrium going here, acetic acid plus hydroxide ion. Okay, so you have to think about what's happening at each in each region of that titration curve. You have to know the chemistry. So anyway, I have Kb for this reaction is going to be, remember the relationship between Ka and Kb is Kw. So Kw over Ka is going to be 1 times 10 to the negative 14, and Ka was 1.8 times 10 to the negative 5. And let me go ahead and do this, calculate this, divided by 1.8 to the negative 5. And that's going to give us 5.6 times 10 to the negative 10 for Kb. Okay? Let me just make sure that 1 divided by, okay, that's correct. Okay, so we have 5.6 times 10 to the negative 10. So now I set up an ICE table, okay, because now we have the hydrolysis of the acetate ion. So here we determined the concentration, okay, so that's 0.25 molar. So we have our ICE table set up. That's going to be minus some amount x, plus x, plus x, and then of course this will be 0.250 minus x, x, and x, okay. I'm going to assume that x is much less than 0.250, so I'm going to assume that 0.250 minus x is approximately 0.250. We'll check the assumption in a few minutes. So now I can set up my Kb expression, and that's equal to 5.6 times 10 to the negative 10, okay, which is going to be equal to x squared over 0.25. Okay, and then what I'm going to do is solve for x, and you're going to have to excuse me a minute while I plug this into my calculator. 25. Okay, and I end up with 1.18 times 10 to the minus 5. Okay, so we have to remember that x is equal to the hydroxide ion concentration. Okay, and of course that's 1.18 times 10 to the minus 5. Let's go ahead and check our assumption. Let's see, 0.25 minus 1.18 times 10 to the negative 5 is about 2.5. So our assumption is justified. You always have to check the assumption. Otherwise, you're going to have to solve the quadratic equation and, you know, use methods to do that. But this is much easier. So my hydroxide ion concentration is 1.18 times 10 to the negative 5. So I can determine my pOH, which is just going to be a negative log of 1.18 times 10 to the negative 5. And let's see what that gives me. 1.18 times 10 to the negative 5. That gives me a pOH of 4.93. Okay, so my pH then is going to be 14 minus 4.93. Okay. And that's going to give me a pH of 9.07. Okay, so 9.07. All right, so let's go ahead and add this to our chart. So now we have the pH at the equivalence point. And again, that is due to the hydrolysis of that acetate ion. So 9.07, okay, at this point. Good. Okay, now let's see. We'll go to part E. And in part E, we're asked for the pH after 21 milliliters of sodium hydroxide have been added. Okay, so this is beyond the equivalence point. All right, so what we need to do here is we need to calculate the hydroxide ion concentration from the added volume and the sodium hydroxide solution concentration, because now all of the acid has been consumed, so the pH is just going to be based on the pH of the solution here. So let's go ahead and determine that. So we have, after 21 milliliters, we have 0.021 liters. And we'll multiply that by the molarity of the sodium hydroxide solution, which was 0.5 molar. Okay, and that's going to give us the number of moles of hydroxide will be 0.021 times 0.5. That's going to give us 0.0105 moles of hydroxide ion. Okay. Okay, so now here's what we have beyond the equivalence point. Let me go ahead and write the reaction again here. Okay, plus OH is going to give us water plus the acetate ion. Okay, so the initial amounts, again, we'll just go ahead and write our initial amounts here in moles. Okay, this will be about zero. Now, we've added 0.0105 moles of hydroxide ion. So the changes will be that's going to be minus 0.0105 moles. Okay, the same here. Okay, and let's see, and this here is going to be plus 0.0105 moles. Okay, so remember, the acetate ion compared to hydroxide ion is a very, very weak base. Okay, so our hydroxide ion concentration is going to be simply this. Hydroxide ion concentration is going to be equal to the 0.5 moles, okay, over the total volume. So that's going to be 20 milliliters plus 21 milliliters, okay, and that's going to give us 0.01 molar in hydroxide ion. So from here we can calculate the pOH. That's going to be a negative log of 0.01 molar, and that's going to give us 2.0. So our pH is going to be 14 minus 2.0, and that's going to give us a pH of about 12. Okay? So let's go ahead then and put this on our chart here. And so after 21 milliliters, our pH is 12. So now I'm ready to sketch the curve, okay? And, you know, again, we started off with, so it's going to look something like this, okay? Here's our steepest part. So our equivalence point here, that was 20 milliliters. So this will be the number of milliliters of titrant. This is our pH. So our pH here at the equivalence point is 9.07. Okay. And initially at 0 milliliters, we started off with a pH of 2.52. And then after about 10 milliliters, okay, so that would go around here, we ended up with a pH of 4.74, okay? And then, of course, after 21 milliliters, okay, that'd be after the equivalence point, okay, we ended up here, we have a pH of 12.0, okay? Not exactly drawn to scale, but you do get the idea, okay? So in the next segment, I'll do the titration of a weak base by a strong acid.